In Chapter 5, we continue to learn about alkenes, about their structure. We're going to practice more nomenclature, and then we're going to start an introduction to the reactivity of alkenes and how they can form new bonds and new bonds can be broken. So, molecular formula. For alkenes, this is the first type of molecule that we would call unsaturated. An alkene has one pi bond, and one pi bond is an indication of 1 degree of unsaturation. So, unsaturation, saturation, these are terms you should be familiar with. A saturated molecule or a saturated hydrocarbon has all single bonds, and it has no pi bonds and no rings. And the degree of unsaturation is determined by counting how many pi bonds and how many rings are present in a molecule. The molecular formula of a molecule can be determined based off of the formula shown in yellow, that for an alkane, a saturated alkane, so we take the formula of a saturated alkane and we subtract 2 hydrogens for every pi bond or ring that is present. And the degree of unsaturation is the total number of pi bonds and rings. So you could say that the molecular formula is 2 times the degree of unsaturation. What we could rewrite the molecular formula of as being, whoa, okay, CnH2n plus 2 minus 2 times the degree of unsaturation. Because you're going to subtract 2 hydrogens for every pi bond or ring. If we multiply by the number of pi bonds or rings, we say 2 times the number of pi bonds or rings, that will equal to the correct number of hydrogens. So, comparing saturated and unsaturated hydrocarbons. Saturated hydrocarbons have no double bonds. They have no lone pairs, and they have no pi bonds. So saturated hydrocarbons cannot act as Lewis bases because they don't have electron pairs to donate or pi bonds to donate. Unsaturated hydrocarbons have 1 or more double bonds. For the nomenclature of alkenes, we covered this minutely in Chapter 4. We are going to replace the ane of the alkane with ene for the alkene. So, for example, the systematic name of a 2-carbon alkene is ethene. For a 3-carbon alkene, we have 1-propene or propene. For a 5-carbon cyclic alkene, we have cyclopentene, and the carbon 1 is always one of the pi bond carbons. We also have cyclohexene for the 6-carbon alkene, cyclic alkene that has 1 pi bond. As with other functional groups, we want the chain to contain the functional group. So the main chain should contain the functional group, and we should give the functional group the lowest possible numbering. But if we have a functional group that is higher priority, such as an alcohol, we will still number and name the chain to give the alcohol the lowest possible numbering. Stereoisomers are named using cis or trans or E or Z prefixes. So we learned how to determine E and Z in Chapter 4, and now we have to apply it to be able to name molecules correctly. If we have two double bonds, we're going to call the molecule a diene. Our examples here are 2,4-heptadiene, because there are 7 carbons. The first pi bond is bonded at carbon 2 to 3. So we write 2 because that's where the pi bond starts. The second pi bond starts at carbon 4 and goes to carbon 5. We write carbon 4 to indicate where the pi bond starts. We can also say we also have 1,3-pentadiene in the middle and 1,3,5-hexatriene at the end. We have to indicate where each pi bond is located with the number of the sp2 carbon that is the first carbon of the pi bond. Number the chain in the direction that gives the functional group the lowest possible number. Okay. So the longest chain of 4 of the pentene shown is 5 carbons, and the carbon 1 is bonded to carbon 2, which is the first pi bond carbon. So this is if we number it from this first methyl group at the left and move to the right, the pi bond gets a number of 2. If we were to start at the right and move to the left, the pi bond would have the number 1, 2, 3. So the pi bond would get a number of 3. We want to start from the other side because 2 is less than 3. If we look at 3-methylpentene, we can determine the longest chain because we know that 2 carbons is more than 1 carbon. And then we can number from the side that is going to give the lowest possible number for all substituents. The pi bond and the branch are both on the left side of the molecule, so we are going to start numbering from the left. Then we have the first case of another functional group other than the alkene. In this case, the functional group is an ether, but it has a lower priority than the alkene, which is the highest priority. We have to choose the longest chain containing the alkene. So the 5-carbon alkane on the other side is not the main chain. We will start numbering from the pi bond and move towards the oxygen. This would give us that the oxygen and its 5 carbons are a prefix called 4-pentoxy. The alkene is located at carbon 1 of a 4-carbon chain, and so this is 4-pentoxy 1-butene. Then we have a 5-carbon diene chain. We can start at carbon 5, at the carbon they have labeled as 5, and have our pi bond start at 2, or we can start at the carbon they have labeled as 1 and the pi bonds start at 1. And this is the better direction. So we want to number this molecule from the right to the left to get a pentadiene with a pi bond at 1 and 3 and a methyl group at 4. 4-methyl 1,3-pentadiene. We state the substituents in alphabetical order. This is the same rule that we have been used previously. Substituents are still stated in alphabetical order. The branch on the methyl branch at the left side of the molecule is closer to the terminus than the ethyl branch at the right side of. Actually, they're the same distance. Okay, the methyl and the ethyl branch are equidistant from the terminal carbons, but the pi bond is closer to the terminal carbon at the left. So we're going to start numbering from the left and go to the right to make the longest possible chain. Incidentally, as a skeletal structure, this would look like the following. That would be the skeletal structure. 1, 2, 3, 4, 5, 6, 7, 8. At carbon 3, we have a methyl group, and at carbon 6, an ethyl group. At carbon 3, we also have our pi bond. So this molecule, listing the groups in alphabetical order, we would write 6-ethyl, followed by 3-methyl, and then 3-octene, because the longest chain is 8 carbons. If we name the molecule at the right, the substituents are bromine at carbon 5, chlorine at carbon 4, and the alkene between carbon 1 and 2. Bromine is alphabetically first, so we would have 5-bromo, then 4-chloro, 1-heptene. If both directions give the same number for the functional group of interest, the correct name has the lowest substituent number overall. So in this case, we have that the pi bond is at carbon 4 whether we start from the right or the left or the right. However, for the substituents, if we start from the right and move to the left, we would have a substituent at carbon 2, the pi bond at carbon 4, and the second substituent at carbon 5. So that would give us substituents and the pi bond at 2, 4, 5. And that's what I get as I number towards the left. If I were to number from right to left, my substituents would say 4-methyl, 4-ene, and 7-methyl. So it would be 4, 7. Because 2 is less than 4 and 5 is less than 7, the substituent should be labeled as 2, 4, 5. You can also do this by adding the numbers together. The red would equal up to 11, and the orange option would equal up to 15. So numbering from the right towards the left is the correct numbering, giving us 2,5-dimethyl-4-octene. We have a second example of numbering from the left or the right, putting the pi bond at carbon 3 from either direction. If we label the substituents starting from the left and moving to the right, we have a substituent at 2, we have the pi bond at 3, and we have another substituent at 4. If we start numbering from the right towards the left, we would have a substituent at 3 for the pi bond, and then at carbon 5. 234 is less than 335, and so the correct numbering would say 2-bromo, 4-methyl, 3-hexene. Nomenclature for cyclic alkenes. A number is not needed to indicate the position of the functional group as a pi bond. For the nomenclature of cyclic alkenes, a number is not needed to denote the position of the alkene functional group. It is always between carbon 1 and carbon 2 of the alkene, as long as the pi bond is the priority functional group. The 3-ethyl cyclopentene shown at the left is numbered such that the pi carbon number 1 will put the ethyl substituent at the lowest possible number. It is always the terminus of the pi bond, so that the pi bond carbons are always C1 and C2 carbons. You cannot have only one of the pi bond carbons be carbon 1 and the other be carbon 6. They have to be carbons 1 and 2. So that if we did number it in the other direction, then this would be 1, this would be 2, then we'd have a 3, 4, and the ethyl group would be at carbon 5. That would not give us the lowest possible numbering. And that is why they chose to number in the direction that they did. You number from the pi bond carbon that is most distant from the group, while the pi bond is closest to the group. You number from the pi bond carbon that is furthest from the group towards the group. From the pi bond carbon furthest from the group towards the group. So we are numbering from the pi carbon furthest from the branch, 1, along the shortest path toward the branch, giving the branch at the position 3, and the name of the molecule as 3-ethyl cyclopentene. For nomenclature of alkenes with 2 groups, you want to number over 2 substituents, 2 branches. You're going to number overall, with the alkene always being at carbon 1, so that all groups have the lowest possible numbering. So let me show you why they have numbered these groups in the way that they have. In the case of the first, we have both the alkene and the chlorine at carbon 1. Then we have a chlorine at carbon 6. If we were to number in the other direction, we would have the following result. 1, 2, 3, 4, 5, 6, in case 1, one of the groups has a lower number than in case 2. So because one of the chlorine gets the number 1 in the first name, we consider that the lowest possible numbering, because 1 is less than 2. That is for the molecule at the left. If we look at the molecule at the right, again, we can number from the pi carbon that has a substituent, or from the pi carbon that does not have a substituent. But you always want to start at the pi carbon that has a substituent. So let's write that down. If the pi carbon has a branch, and this is for rings only, that carbon is carbon 1. In ring.